Okay, continuing where we left off, we're talking about electrolytes, or rather particles in water, as opposed to non-electrolytes and strong electrolytes, and what happens to the freezing point of water and the boiling point of water. All right. And how it changes because of the presence of electrolytes. So if you have a non-electrolyte, mole for mole, the amount of particles formed in water are much less compared to a strong electrolyte. So the more particles you can generate in water, the more you can depress the freezing point. Okay. All right, so here in table 9.13, it's an effective comparison of what happens when you add different types of electrolytes to water. Pure water has 0 particles of solute, and so the freezing point is, or melting point uh, is 0 degrees. The boiling point is 100 degrees. Now, if you add a mole of this ethylene glycol, which is a non-electrolyte, that means you're adding to a kilogram of water 1 mole of the solute, the glycol. All right. So if you add 1 mole to a kilogram of water, its freezing point goes down by a couple of degrees. All right. So it's negative 1.86. Its boiling point increases by 0.5, by half a degree. All right. Now, if you add a mole of sodium chloride, on the other hand, now in that kilogram of water, you're generating 1 mole of the sodium ion and 1 mole of the chloride ion, because of the fact that sodium chloride is a strong electrolyte. So you're generating 2 moles of solute, 2 moles of particles. All right. So that's 2 times the negative 1.86. All right. So the freezing point has come down by almost 4 degrees. All right. Whereas the boiling point of that kilogram of water has gone up by 1 degree. Okay. If, on the other hand, you add a mole of calcium chloride, so you get 1 mole of the calcium and 2 moles of the chlorides, a total of 3 moles of particles. All right. So that's 3 times 2, roughly. So freezing point has decreased by 6 degrees. All right. It's gone down to negative 6. And the boiling point has increased 0.5 times 3, so 1.5 degrees. All right. Now, this is important. Calcium chloride is what is used to de-ice the roads and to keep it from freezing up. All right. And so you can see that it really brings down the freezing point to negative 6 degrees, right? From 0 degrees to negative 6 degrees. So the roads can remain clear in winter, okay? All right, so now we can use these numbers for depression of freezing point and elevation of boiling point to determine for different amounts of solute what they will be. Okay. All right, so here calcium chloride, as I said, is spread on the highways to melt ice and to keep the roads clear. So if you have a half a mole of calcium chloride in 1 kilogram of water, all right. So if you have 1 mole of calcium chloride, if we go back to that table, you see 1 mole, that means you're generating 3 moles of particles, right? So the freezing point is going down by almost negative 6. Suppose you just had half a mole, all right? That means you have half this amount, so that's 1.5, okay? So 1.5 times the negative 1.86, all right? So it'll be half this, all right? Instead of negative 6, it is going to go to negative 3, all right? So let's see how that works out, okay? So 1 mole of calcium chloride is able to generate 3 moles of the solute particles in water, okay? So half a mole times 3, and for each mole it goes down by 1.86 degrees, all right? So 0.5 times 3 times the 1.86, so about 2.8 degrees centigrade. So it'll get depressed by 2.8. So from 0 it will go to negative 2.8 or negative 3 approximately, okay? All right, osmosis. Osmosis is a phenomena where you have, say, two solutions separated by a semi-permeable membrane. So here you can see it's pure water on one side, and then you have a solution which has some amount of solute sugar, right? Now what happens is you have a lot of water here and not enough water on the other side where the sugar is, because of the fact that some of that space is now being occupied by the solute particles, all right? So water is going to flow from a direction of more water to less water, all right? So this flow keeps happening until the what happens is the level of water here will start steadily rising. The level of water here will start decreasing. But at some point, what will happen is it will not allow for the water level to rise up, all right? That's because what happens is there is a certain amount of pressure here, there's a certain amount of pressure here, all right? So the pressure here will kind of equalize, and then it'll prevent more water from coming in. That doesn't mean that the flow of water has stopped. There is a constant, steady flow of water, and equilibrium is reached, all right? Okay. So one side is going to rise up a little bit until such time that the flow of water in both directions equalizes, all right? So osmotic pressure is what prevents more water to come in and keep on increasing that level, all right? So osmotic pressure is equal to the pressure that would prevent that flow of additional water into the more concentrated solution, all right? Now, if you have more stuff, just like with the gas particles, all right, more stuff means there's going to be more osmotic pressure, all right? So the more concentrated, more particles, dissolved particles are in a solution, that solution is going to have a higher osmotic pressure as compared with a solution which has 0 to no particles, all right? Okay. So over time, you can see the level in the sucrose solution, the water level starts rising. But at some point, osmotic pressure prevents the flow of more water coming in. However, there is a back and forth flowing of water at a constant, steady rate. Okay, and that's called as equilibrium. So there's a process called as reverse osmosis. Now this comes in handy in places where there's where it's hard to get fresh water. Like for example, in countries which are surrounded by sea on all sides and very little very little sources of fresh water is available to supply the population. What they can then do is do a process called as reverse osmosis. So they will apply pressure on this side, all right, where it's more concentrated. Imagine this was a salt solution, all right. So they will apply enough pressure to overcome the osmotic pressure of the solution, and then force the water to go in the reverse direction, all right. So that's how they can take salt water and push all the water out of that salt water into the other direction to create fresh water. Okay, and that's process is called as reverse osmosis, where you apply a pressure greater than osmotic pressure, forcing water to go in the reverse way. All right. Okay, so it's actually going from an area of lower water to an area of higher water, all right, leaving behind all that salt, etc. Okay. Now this process is used in desalination plants to obtain pure water from seawater, and it requires a lot of energy. Okay. All right, osmosis can be applied to any cells, especially red blood cells. All right. So this is used, of course, in hospitals, especially with IV solutions and fluids, body fluids, etc. Because each of those fluids has its own osmotic pressure. Remember, the more stuff a fluid has, more osmotic pressure. All right. So a normal red blood cell should have 5% mass by volume glucose. That means 5 grams of glucose per 100 ml of the fluid. All right, and 0.9 grams of sodium chloride per 100 ml. All right. So that would be called as isotonic. All right. This is the equilibrium condition. This is what keeps the red blood cell intact. Okay. So tonic just means pressure. So this is the correct osmotic pressure for a red blood cell. All right. So here you have 3 pictures. You have an isotonic. That means you have 5% glucose outside and 0.9% NaCl outside and inside. So the red blood cell is intact. Now you can have a hypotonic solution, like say if it's just pure water, distilled water, all right? That means there's no solute at all. There's more stuff inside the cell, all right? So osmotic pressure inside the cell is higher because there's more glucose and sodium chloride inside the cell. So more water on the outside, less water on the inside, which is inside the cell. So water is going to flow in, and the cells are going to swell up, and then finally they're going to burst, and that's called as hemolysis. Hem because it's red blood cell, hemoglobin, and lysis is breaking up of that red blood cell. Now, on the other hand, if you had a very salty solution, all right, like a 10% sodium chloride, that would be called as hypertonic. Inside the cell, it's only 0.9% sodium chloride. Outside the cell, it's 10%. That means it's less water outside the cell, more water inside the cell, all right? So again, water is going to flow from a place of more water to less water. So it's going to go outside from the cell, all right? So water is going to flow out of the cell, and the cell is going to shrink up, and that's called as crenation, okay? So in a hypotonic solution, the water is flowing into the cell, causing it to swell up and burst, hemolysis. In a hypertonic solution, water is flowing out of the cell, causing it to shrink, and that's called as crenation. All right, let's stop here.